Welcome back. Today I'll be talking about discrete and finite sample space example. Last time we talked about discrete and finite space sample space and also talked about continuous and infinite sample space. But today we'll talk about discrete but infinite sample space. Let's say we carried out an experiment that will provide us arbitrary positive number. Let's say we tossed a coin and we will count how many times you have to toss the coins to get a head. We can get a head in first toss, we can get a head in second toss, and this can go on to infinite number of times. Therefore, we have a sample space where number of tosses can range from 1 to infinity. This is our sample space. Next step is to define probability law for our sample space. And probability law should apply to all events in sample space. But we will define probability law for just one single event. We'll say that probability law for one single event or one single subset of this set is 1.5 power to n, where n is an entry in this subset. N is an entry in this subset. N is an entry in this set, in the sample space. Now we have to see whether this our probability law makes any sense. One thing we can check is whether the sum of this probability law sum up to 1. How do we do that? We say that we are saying that n is equal to 1 to infinity, and probability of each event is 1 by 2 power to n, 1 by 2n. We'll factor out 1 by 2, which will give us n is equal to 0 to infinity 1 by 2 n. What we have at hand is a geometric series. This is a geometric series. Therefore, this is a geometric series. This is a geometric series. Therefore, this is equal to 1 by 2 times 1, 1.5, which is equal to 2 by 1, which is equal to 1. Therefore, this sums to 1. That's why our probability law makes sense. Third step is to calculate the probability law is to define some event. An event we are defining is an outcome which are even. That is, events which have even numbers, such as a set which has even numbers, infinite set which has even number of um, even number of tosses. Just to say it mathematically, outcome is even, meaning it is set when we have we get head after 2 toss, 4 toss, 6 toss, etc. to infinity. That is the event we are talking about. Now we need to calculate the probability of this event. What we can do is we can chunk this set into smaller steps with each set with the single element. That is, we can divide this set into smaller set with single element and union them. And union them. What we see is that this set, these little sets are distinct in nature because there is no, all these numbers are different. If you look it properly, all these number are different. Now let's stop for a moment and think about it. Can we apply the law of additivity axiom here? Can we add that? Whether or not if we can use it, let's use it and see what happens. Let's use the additive axiom of the sets here. That would give us, so that since they are disjoint, we can use the additive axiom to give us probability of each single element. And that would give us probability of 2 plus probability of 4 plus probability of 6, etc. Here we have it. Next step is to actually calculate the probability of each of these expression. Here, what is the probability of 2? Probability of 2 is 1 by 2 and is equal is square by 2. Probability of 4 is 1 by 2 power to 4. Probability of 6 is 1 by 2 probability of 6, etc. Next step, we can take 1 by 4 common. That would give us 1 as a first term. Second term is 2 to power 2 and third term is 2 to power 4, etc. This is what we get. Now, if you look carefully, this is also a geometric series of 2 by n. Isn't that true? It is. Therefore, we can also do the same thing as we did before, saying that this is equal to 2 by 1 which is equal to 1 by 4 divide, that is 1 by 4, 2 by 1, which is equal to 1 by 2. That's what you get. Okay, I think I made a mistake here. Instead of this, we can say that when we take this power, we can do for 4 by 1 and 4 by 2. That would give us 4n, which is equal to 1 by 3. So that's the answer for this. Leaving the calculation details aside, let's go back and see whether is our calculation correct. Can we use the additive axiom or additive property here for sets? We know that additive axiom or additive property only applies to finite sets, but here we have infinite number of sets. Therefore, we cannot conveniently use additive property here. It's not really allowed. In one hand, we really want to use additive property here, but on the other hand, we cannot use it. Therefore, we need to introduce one additional axiom that would allow this kind of calculation. That is much for today. Let's quickly summarize what we discussed. We discussed about probability law for discrete but finite infinite sample space, and for that we talked about the experiment where it is a set of infinite number generated by tossing a coin to get a first head. Thank you so much.